Returning to Faraday's experiment, we concluded that current could be induced to flow in a coil surrounding a magnetic material where the magnetic field in that material was changing. More specifically, an electromotive force exists in the coil which causes current to flow. It turns out that we can generate the same electromotive force in the wire by keeping the magnetic field constant and changing the position of the wire. For example, consider the diagram shown here. We have a wire that is suspended in a magnetic field, and we will now move the wire in a downward direction. This will result in voltage potential from one end of the wire to the other. But what is the polarity of this voltage? Well, to figure this out, we use something called the left-hand rule. Simply stated, if you line up the index finger of your left hand to point in the same direction as the magnetic field, and your middle finger is pointing in the direction of motion, then your thumb will point to the positive end of the wire. So try this for yourself and see what happens. Take your left hand and line up your index finger to point in the direction of the magnetic field. Okay, now without changing the direction your index finger is pointing, make your middle finger point down, which is the direction of motion. Which way is your thumb pointing? If you did everything correctly, it should be pointing at the back end of the wire. This will be the positive end of the wire. See how much fun this stuff is? However, just be careful about doing these hand gestures in public, as people might think you're a little strange. Let's do the same thing we did with the right-hand rule, and let's see how we can apply what we've just learned to a rotating system. In this case, we can see the cross-section of a cylinder, which is once again rotating in a uniform magnetic field. Down the length of the cylinder on the left side, we have a wire segment labeled A, and on the right side we have another wire segment labeled B. Also, let's assume that these two wire segments are connected together behind the cylinder so as to form a loop of wire. We will define the flux which is threading through the center of this loop as phi, the Greek letter phi. From Faraday's law, we see that the voltage which will be generated from this end of wire A to this end of wire B is equal to the change of the flux which is threading through the loop. But wait a minute. If the magnetic field is said to be uniform, then how can the flux in the loop be changing? The answer is to change the cross-sectional area of the loop with respect to the magnetic field by rotating the loop. Let's watch what happens as we spin this loop of wire in the counterclockwise direction. From this animation, you can see that the flux in the loop changes most rapidly when the loop of wire is straight up and down, which is right where the loop area collapses to zero. As predicted from Faraday's law, this corresponds to the point where the voltage is also the highest. Conversely, when the loop is horizontal, the flux in the loop is maximum, but the change in flux in the loop is zero during this time. And this results in the voltage being zero when this occurs. Now what do you think would happen if instead of a single loop of wire, there were N loops of wire all connected together in series? The answer is that the voltages from each loop add together in series, creating a much higher voltage. This has the same effect as multiplying the flux in the loop by a factor of N. In fact, the flux in the loop when multiplied by N is referred to by another term called flux linkage, and we typically represent that by the symbol lambda. So really, Faraday's law can be rewritten in terms of the flux linkage as shown here. Before leaving this slide, I want to make one more observation about Faraday's law as it applies to rotating machines. You see, the change in flux linkage with respect to time can really be busted up into two separate terms. One term is how much the flux linkage changes as a function of the rotational angle, which is related to the number of turns, the field strength, and the geometry of the machine. This term also accounts for the AC waveform as the machine rotates. But notice that all of the factors that go into this term are pretty much constant for a given machine. The second term, however, describes how much the rotational angle is changing as a function of time, which is really the rotational velocity of the coil. So if we ignore the AC component of the first term for a moment, we see that the voltage magnitude out of the coil is equal to the rotational velocity of the coil times a term which is pretty much fixed for a given machine. This term is often referred to as the back EMF constant of the machine. You may have noticed that the mechanical structure for the motor presented earlier in this tutorial and the mechanical structure of the generator we just discussed are absolutely identical. So this raises the question, is there really any difference between a motor and a generator? The answer is, not really. It just depends on how you use them. For example, in some hydroelectric applications, the water from a lake runs over a dam during the day, which turns dynamos acting as generators to generate electricity. But at night, when the electricity rates are cheaper, those same dynamos are used as motors to pump the water from the lower lake or river back up to the higher lake to be reused the following day. It's pretty ingenious. Anyway, to illustrate my point about motors and generators, let's take a look at the following demonstration. Okay, let's take a walk over to the lab bench here and see if we can demonstrate this principle. Now, this is a contraption that I put together for this purpose. It actually consists of two brushed DC motors which are connected together at right angles through this gear arrangement here. And we also have, for our load, we got these two 6-volt light bulbs that are actually wired together in series. So the question that we are trying to answer is which one is the motor and which one is the generator. So if you come on into the lab bench here a little closer, and we'll hook this up. I'll start by powering this motor right here with my power supply. There we go. And now, let's see if this motor can actually be made to work as a generator in this case. And as you can see, this one's clearly acting as a motor, but this one now is acting as a generator to power the load. But we will also see that it really doesn't matter because I can also power up this motor and hook my load in over here. And it has exactly the same effect. So what we see here is that really every motor is a generator and every generator is a motor. It really doesn't matter. It only depends on how you use them.